Okay, so the next topic we should discuss is the analytic geometry of lines and planes. And I think here we first come up against our first exposure of the two competing viewpoints for describing geometric objects. I would say that there is the explicit viewpoint and there's the implicit viewpoint. Usually we call something described by the explicit viewpoint to be a parameterization or a parametric description of the object, whereas the other implicit viewpoint, the object is typically described as a solution set to some equation or equations. Now, so to start with, in 3 dimensions, we could describe a line parametrically by r of t is equal to some base point r naught plus tv. I'll draw a picture down here of that. So basically what's going on is, the line is somewhere out there in space, all right? And at time 0, r of 0 is what? We plug in time 0, r of 0 is equal to r sub naught, so it's like the base point for the line. And then as time goes on, we add copies of the direction vector v. So this v would be something like that. So if that's the case, if that's how long v is, then like over here, r naught plus v would give us that point right there would be r of time 1, which would be r naught plus v, for example. And as the time goes on, you trace out this line, in 3 dimensions. So now I'm describing it in a vector sense, right? I'm giving you the vector parameterization. You could also talk about the scalar parameterization of the line, and that would look something like this, something like x equals to x naught plus tv1, y equals to y naught plus tv2, z equals to z naught plus tv3. That's really just a different notation for what I've written up here, where I'm saying that v is v1, v2, v3, the direction vector. We do assume that the direction vector is non-zero. All right. The base point r0 could be 0. This line could go through the origin. But that's all it takes. You need a base point and a direction vector, and that describes a line in 3 dimensions. And this is these 3 equations are the parametric equations to describe the line, but I really prefer to think of it in a vector sense. So r of t is r naught plus tv. Now, if you take these parametric equations, right, and you solve them for t, and I guess over here I've used this as being A, this as being B, this being C for this side. So if you put that A, B, C, and you solve this for t, solve that for t, solve this for t, you'd get x minus x naught over A equals to y minus y naught over B equals to z minus z naught over C equals to t. This is the so-called symmetric equations for a line. I almost never use these. I don't like them because they're not general. If any of A, B, or C is 0, then they cease to make sense, and then the symmetric equations of a line, well, they're no longer symmetric. You gotta if one of these components is 0, then you have something like x, like if v1 is 0, you have x equals to x naught as one of your parametric equations. All right, so anyway, just to take a step back for a second, in 3 dimensions, we have a line. A line is a one-dimensional object, so it takes 2 equations to fix a line. But just one parameter, because the line is essentially one-dimensional, and t you could think of as being, in some sense, the coordinate along that line. So we could think of t that way. T is like the coordinate along the line. So that's lines. But the other thing we can talk about is a plane. And so a plane, from a parametric perspective, we can parameterize the plane by the base point plus s times a plus t times b. Here, a and b are tangent to the plane. Sometimes we'll say that they lie in the plane, all right? So that's the parameterization. So the plane is two-dimensional. It requires two parameters. I'll draw a picture of this in an upcoming, well, yeah, I can fit it. Let's see if I can fit it here. So if I'm so foolish as to try to draw the plane, it goes on and on, but I'm just drawing it like that, all right? So let's see here. So this R naught is like some particular point on the plane. I call it the base point. Not just me, lots of people call it the base point. And then A and B are vectors that lie on that plane. So I might make A go like, maybe A goes like this. You can move it around, right? And maybe B goes like this. They don't have to be perpendicular, but they do have to actually lie in the plane. Tangent vectors. So R naught plus A plus B, that brings you out to like that point on the plane right there. And for what it's worth, that would be R of S equals to 1, T equals to 1. So that's how that works. You can think about S and T as kind of like laying out coordinates on the plane. As S varies, we go in the A direction. As T varies, we go in the B direction. And we can get to any point in the plane by starting at R naught and adding copies of A and B as appropriate. So that's a parameterization of the plane. In contrast, the plane is two-dimensional. In 3 dimensions, we just need one equation for the plane. And so this is the standard equation for the plane. Something like A times x minus x naught plus B times y minus y naught plus C times z minus z naught equal to 0. And here, the vectors which were tangent, A and B, the cross product of those guys would give us this ABC. And I should mention that that has a special name, which we'd like to know. This ABC is the so-called normal to the plane. All right. So this is the standard standard equation of the plane. So anyway, long story short here, guys. I could talk about this a lot longer, but I'm just going to try to get to the point, which is that we prefer this viewpoint for lines. This is like our happy place. This is the nice way to describe a line. I prefer to use that right here. And I try to use the equation to describe a plane because I just need one equation and I can describe the plane. However, we do find ourselves needing to parameterize a plane a little bit later in the course, so this is like also important. And I use this in the notes, you know, between pages 50 and 75 to build examples, but more about that later. So let me try to derive this equation for you from a geometric perspective, but before I do that, I'd just like to point out in 2 dimensions, which I think you've already talked about in Calculus 2, we just have an x and a y coordinate, right? So the parametric viewpoint is pretty much the same, except that, you know, the x would be equal to like x naught plus tv1, y would be equal to y naught plus tv2. You could solve both of these for t, like t would be equal to x minus x naught over v1 would be equal to y minus y naught over v2 if you were to do that. And then you could solve that for y, like y is equal to v2 times x minus x naught over v1 plus y naught. In other words, y is equal to v2 over v1, which I called m, times x minus x naught plus y naught, assuming that v1 is non-zero. So there you go. That's how we can get from the parametric equations for a line to the so-called Cartesian equation for the line. But again, this is still more general because this allows for vertical lines, whereas this formulation can only deal with lines that don't have that are not vertical. Vertical being the case that v1 is 0. So anyway, hopefully you've already talked about parametrized curves in the plane. If you haven't, read my pages 50 to 75. There is way more than you need there. So don't be intimidated by my parametrization discussion on pages 50 to 75. Parameterizing curves and surfaces is an art form, and I have a lot to say there, and not all of it's needed. Again, I would focus your energy on the homework and not worry about everything that's said there too much. I'd like you to look through it and kind of see what's there, but I don't expect you to understand all of that. So, all right, moving on. Let's go back and try to take a deeper look at that formula. 14, page 14 here. All right, so let's see if we can understand that formula and work an example or two here. So we've got some plane, right? Let's draw a picture of it like this. And I'll put the coordinate system down here. X, Y, Z, right? And what I want to understand is, like, from a geometric perspective, why is the equation what we found? So the normal to the plane, right? I'll use the ABC that I introduced back there. So it's something like this. It's perpendicular to the plane, the normal vector, which we'll use A, B, C, right? And I'm also supposing I'm anchoring that normal vector to the base point. So the base point right here, R naught, right? So we could envision that. I guess this could not, that doesn't have to be dotted, but this has to, I'm trying to make that dotted because it's under the plane, like that. So there's my base point, right? And then what I want to do is think about any other point on the plane, like this one, right? I'll call that R. So we don't know what that, I'm going to call it X, Y, Z because we're not, we're trying to characterize if X, Y, and Z is a point on the plane, right, which corresponds to the vector pointing from the origin, right? Draw the vector first, draw the point second if I was smarter. Then what can we say about X, Y, Z, right? How does that relate to this normal and the base point? So the answer is simply in the tip-to-tail vector addition and such that we looked at. So if we look at this vector here, right, that goes from R naught to R, what vector is this? This is R minus R naught, right? And that's a vector. So R minus R naught is a vector tangent to the plane. And I'm going to label the plane P. So this plane is P. All right. So that's my point to you. R minus R naught is a vector tangent to the plane P, right? But what else can we notice? N is perpendicular to tangent vectors. In fact, that's really what defines it to be the normal. The normal is perpendicular to all the vectors which are tangent in the plane. But we know what that means. That means that the dot product, right, the dot product of the normal vector and this tangent vector has to be 0, right? But the normal vector is A, B, C, and R minus R naught is X minus X naught. y minus y naught, z minus z naught. That's all equal to 0. Now here I slipped something in to the discussion, which is that r naught is given in terms of the coordinates. I mean the components of r naught is x naught, y naught, and z naught. Excuse me. And so multiply that out, and what you got? You got a times x minus x naught plus b times y minus y naught plus c times z minus z naught equal to 0. And that is the standard equation for a plane. Now, of course, you could also do it like this: ax plus by plus cz equals to d, where d is all that stuff. I mean, in this case, d is ax naught plus by naught plus cz naught, you know? But so if you're given an equation, you can like straight up read, you know, the normal of the plane. You're like, what do you mean? What do you mean? What are you talking about? Well, for example, if somebody says, find the normal of plane with equation 3x minus 2y equals to 8, you just look at this and go, aha. So that's 3 times x minus 2 times y. Use your imagination. 0 times z equals to 8. So therefore, the normal vector to that plane is 3 minus 2, 0. Simple as that. You just have to look at the coefficients and you can read off the normal. Now you might ask other questions like, okay, that's great. There's a plane with normal 3 minus 2, 0. What are vectors which are tangent to that plane? How would we figure that out? If we have a plane, we know the normal, how do we figure out what the tangent vectors to the plane are? Any ideas? In other words, given a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals to 0. Suppose that describes the plane P. How to find tangents. How to find tangent vectors. So I think that's a good question to ask, because if you can find tangent vectors, then you can parameterize the plane, and that's something we might want to do. So let's look at a specific example, and I'll kind of share my trade secret with you, if you will. So here it is. It's not that complicated, really. So let's say 3x minus 2y plus z equal to 18, whatever. So I look at that, I go, aha, so the normal is 3 minus 2, 1, right? So if I'm looking for tangent vectors, and let's name the tangent vector, we need to give it some letters. So let's say, I'm trying to think of some letters I haven't used yet. How about some Greek letters? Alpha, beta, gamma. This needs to be perpendicular to the normal, right? So we're looking for 3 minus 2, 1 dotted with alpha, beta, gamma has to be 0. We need to see if we can solve that in order to find the vectors. And so what you're looking at is 3 alpha minus 2 beta plus gamma equal to 0. Now, you may never faced an equation quite like this before, but you should have, because you had linear algebra. We could do something simple, like just say, okay, so gamma is 2 beta minus 3 alpha. And what that basically means is, you know, we can choose whatever we like for beta and alpha, and it'll give us a different gamma, right? So like, easy choice. Alpha equal to 1, beta equal to 0. Alpha equal to 0, beta equal to 1. This gives us gamma equal to what? Excuse me. If we put beta equal to 0 and alpha equal to 1, we get -3. If we put alpha equal to 0 and beta equal to 1, we get gamma equal to 2. In other words, we've found tangent vectors of, let's see here, I said alpha was 1, beta was 0, gamma was -3, and the other one was what? It was 0, 1, 2. I can think of those as like the vector A and the vector B I talked about in the previous page. So if I can do this, then I can parameterize plane. Right? I need a base point. What's a base point? Oops, I still need to find a base point before I can parameterize it, don't I? How do you find a base point? So you just need to find any point on the plane. So what I usually do is I do something like lazy. I just say, okay, suppose y and z are both 0. If y and z are both 0, I get 3x equals to 18, which tells me that x equals to 6. So basically just think a little bit and set y equals to z equals to 0. That implies that 6, 0, 0 is a point on the plane. So therefore, we have everything we need. R of s comma t parameterizes the plane with 6, 0, 0 plus s times 1, 0, minus 3 plus t times 0, 1, 2. So if I ask you to parameterize a plane, this is a strategy you can use. And you know, this algebra I went through here, there are other examples where it's like even easier to see. Like sometimes you can just look at the vector and like just kind of like figure out in your mind other vectors which are perpendicular, right? Like if you start thinking about this, the idea of choosing 1 and -3 and making the middle one 0 to make something perpendicular, it's kind of unsurprising. And using 0, 1, 2 to make it perpendicular, that's also kind of like, oh, I could have done that without doing this algebra. So this algebra doesn't have to be shown if you can just see your way from this to the green vectors and go, aha, A is going to be perpendicular to that, B is going to be perpendicular to that. The key is you need two independent perpendicular vectors to the normal vector in order to get tangent vectors to the plane. And so there it is, that's a parameterization of the plane. Let me show you another standard problem that we often face concerning planes. And so this is a time-honored problem, and if you can work this problem with confidence, you're in a pretty good place for this course in terms of this material. So the problem is this. Given 3 points, find equation of plane. All right. So, like generically speaking, here's like generic strategy. So what you do, like suppose you're given points P, Q, and R. I basically just think about it like this. Okay, so I've got point P, I got point Q, I've got point R. This is just a heuristic picture of it. Now I'm trying to find the equation of the plane P. So what I can do is connect the points by displacement vectors. And if you think about it, oh, my computer's trying to unplug itself. Ha, caught you. So if I use P as the base point, I can think about, oh no, come on, computer. All right, I can use this as like, you know, the PQ vector. And I can think of that as like that A vector I was talking about before, right? And This guy down here, I could use as another tangent vector to the plane PR, right? And if you think about it, of course, the normal vector, I want a normal vector, right? I want a normal vector to be perpendicular to those two guys. So an obvious choice would be like PR crossed with PQ, right? Take the cross product of those two vectors. That gives me a vector which is perpendicular, and so this can serve as the normal. To the plane. And how do we calculate PQ? Well, we go back to the basics. PQ is simply Q minus P, and PR is R minus P. And that's basically the strategy. Let me put it into practice here for an explicit example. Let's look at the point 1, 2, 3, and that's my P. And how about 4 minus 8, 0 for Q, and 6, 9, 7 for R. So let's see here. What's my PQ vector? PQ is supposed to be 4 minus 8, 0, minus 1, 2, 3. PR would be 6, 9, 7, minus the base point 1, 2, 3. All right, so what are those? 4 minus 1 is 3. Minus 8 minus 2 is minus 10. 0 minus 3 is minus 3. 5. 9 minus 2 is 7. 7 minus 3 is 4. Right? Now, pesky thing here is we got to calculate the normal as, the cross product of those, so we can use the determinant of x hat, y hat, z hat. We've got a 3 minus 10 minus 3, a 5, a 7, a 4. All right. So what is that? For the x hat one, I get minus 40 plus 21. I get minus 12 minus a minus 15. Always watch out for that sign. We need to check our answer when we get through this. 21 minus a minus 50 is plus 50. All right, so allegedly the normal vector is minus 19, 3, 3, and 71. Not sure I believe that just yet. Let's check it. Let's take the dot product of n with these two guys, right? For lack of imagination, I'm going to call that one A, and I'm going to call this one B. So is A dot n equal to 0? Is B dot n equal to 0? Because they should both be 0 if we did the cross product right. Let's think through it. 3 times minus 19 is 3 less than 3 times 20, which is minus 57. Minus 57 minus 30 is minus 87, I think. Oh, man. No, I don't think it's working out. So that means I've made a mistake somewhere. 3 times 70 is 210. It's minus 200 and, minus 213. I suspect that was supposed to be a minus instead of a, when you think through the sign there. So I've got an overall minus from the y hat term, and then minus minus 12. Yeah, there's 3 minuses on that. That's supposed to be a, that's supposed to be a, I'm missing a minus. I should write it like this. So that makes this actually minus 27. All right, so let's try it out. Minus 19 times 3 minus 10 times minus 27 minus 3 times 71. So this middle one gives us 270. And this is 213. And this is minus 57. So that gives you 0. All right, so I mean, like I told you guys, we got to check the cross product. It's so easy to make a mistake there. And anyway, but we got what we need now, so we'll use P equal to like the base point for the equation. And so what we got is minus 19 times x minus 1 minus 27 times y minus 2 plus 71 times z minus 3. There you go. That's the equation of the plane that has those 3 points. And then you can start asking other questions about the plane if you're interested, like does this plane go through the origin? How would you decide whether or not this plane goes through the origin? Well, plug the origin in, right? So plug in x equals to y equals z equal to 0, right? Then you're left with 19 plus 54 minus 213, which is not equal to 0. So no, this plane does not go through the origin. Of course, another way you could see that would just be to do minus 19x minus 27y plus 71z equals to, well, minus 19 minus 54 plus 213, right? So this quantity, if this is not equal to 0, then 0, 0, 0 is not on a plane. I'm saying generically a plane like ax plus by plus cz equals to d. If you plug in x, y, z, be 0, you must get d equal to 0. So generically speaking, if we write the plane in that kind of format, if the d term is non-zero, the plane doesn't go through the origin. All right, well, those are the basics about lines. I haven't said much about lines, and I'll say more about them when we get to the places where we're using them more. But I think that's a good starting point for us, and I'm gonna stop right here for now.